Welcome to another discussion about modern geometry. For our first topic, we have exploring Euclidean versus non-Euclidean geometry. This topic introduces the fundamental differences between Euclidean geometry and non-Euclidean geometries, such as spherical and hyperbolic. It discusses how assumptions like the sum of angles in a triangle change depending on the space curvature. Students explore real-world applications including navigation and general relativity to understand the practical importance of different geometrical models.
So, we've been learning a lot about geometry, and I just realized that the geometry we learn in school is called Euclidean geometry. It's the one where we assume the space is flat and follow familiar rules like the sum of the angles in a triangle being a 180 degrees. But I'm curious, what really makes Euclidean geometry different from non Euclidean ones, like spherical or hyperbolic geometry?
Great question. The key difference lies in the nature of the space itself. In Euclidean geometry, we deal with flat space, which means the principles we use, like parallel lines never meeting and the angle sum of a triangle being 180 degrees, always hold true. But when we move to non-Euclidean geometries, the properties shift. For instance, on a sphere, the sum of the angles in a triangle can actually exceed 180 degrees.
Wait, so if we drew a triangle on the surface of a globe, say between three cities, the angles would add up to more than 180 degrees?
Exactly, and that's because the surface of the globe is curved. In spherical geometry, the curvature is positive, so triangles have larger internal angles. But in hyperbolic geometry, which you can think of as a saddle-shaped or negative curved space, the angle sum of a triangle is always less than 180 degrees.
Interesting. That leads me to a question. Why do these different types of geometry matter and where do we see them in real world applications?
Excellent Hat's question. The significance of these geometries goes beyond just theoretical mathematics. For example, spherical geometry is crucial for navigation and understanding the Earth's surface. When we chart the shortest path between 2 points in a globe, we use what's called a great circle route, which is a principle derived from spherical geometry. Hyperbolic geometry, on the other hand, plays a major role in modern physics, like in Einstein's theory of general relativity, where space is curved by massive objects.
Wow, that makes sense. It's if hyperbolic geometry helps in understanding the universe's structure, how do mathematicians visualize or work with such saddle shaped space?
That's a tough one. Visualizing hyperbolic space isn't easy because we're so accustomed to flat or positively curved spaces. But mathematicians use models like the Poincare disk model to represent hyperbolic geometry in a 2D form. In this model, lines are drawn as arcs that are perpendicular to the boundary of the disk. And an interesting thing is that from any given point, you can draw infinitely many lines that don't intersect a given line. So parallel lines behave very differently than in Euclidean geometry.
That's fascinating. So, if the rules change that much, does it mean that the basic postulates of geometry change too?
Yes, and that's the main point. Euclidean geometry relies on Euclid's five postulates, with the fifth one being the parallel postulate, which states that through a point not on a line, there is exactly one line parallel to the given line. In hyperbolic geometry, these postulates doesn't hold. Instead, there are infinitely many parallel lines through a given point that do not intersect the original line.
That completely changes how we think about parallelism. Here's another hot question. Why was Euclidean geometry considered the default for so long, and why did mathematicians resist the idea of non Euclidean geometries?
That's a great question, and lets us dive into the history of mathematics. Euclidean geometry was considered the gold standard for thousands of years because it was simple and matched our everyday experiences. The fifth postulate, or parallel postulate, was debated and studied because it felt less intuitive than the others. Mathematicians like Gauss, Lobachevsky, and Bolyai worked on it independently and found that if you deny this postulate, you can still have a consistent geometry, hence the birth of hyperbolic geometry. However, many early mathematicians were hesitant to publish their findings due to fear of criticism and the prevailing belief that Euclidean geometry was absolute.
I see. It's almost like they were challenging a deeply held belief system, right?
Exactly, and it was revolutionary at the time to even suggest that space could be anything other than flat. But these discoveries ultimately broadened our understanding of the universe. For instance, when we look at the Earth on a small scale, it appears flat, so Euclidean geometry works well. But on a larger scale, like over continents or in space, we need spherical or even hyperbolic models to accurately represent reality.
This makes me wonder, how do we teach or apply these concepts without overwhelming students who have only learned Euclidean geometry?
Good question. One approach is to start with small relatable examples, like using maps to explain spherical geometry. For hyperbolic geometry, visual aids like the Poincare disk or interactive digital tools can help bridge the gap. It's also important to emphasize that these concepts builds on, rather than replace Euclidean geometry, showing that non-Euclidean geometries are just extensions that apply to different contexts.
That's really helpful. One last hot question. If we only learned Euclidean geometry, what important insights or advancements would we miss out on?
We would miss out on understanding how space behaves on a cosmic scale and the principles behind general relativity. Hyperbolic and spherical geometries allows us to explore concepts like the shape of the universe, gravitational effects, and even complex networks in hyperbolic space, which are relevant in areas like data science and cybersecurity. So, learning non-Euclidean geometries expands our perspective and enhances our problem-solving toolkit for various scientific fields.
Thanks. That really clears up a lot. Geometry is so much deeper than just lines and angles on paper.
Absolutely. It's like peeking into the underlying fabric of how we understand the space itself. Topic 2 is all about understanding parallelism in non-Euclidean spaces. This topic delves in how the concept of parallel lines differs in Euclidean, hyperbolic, and elliptic geometries. It covers the altered Pythagorean theorem in hyperbolic space, the significance of curved surfaces in navigation, and how non-Euclidean ideas impact fields like cosmology, art, and architecture. The discussion emphasizes the shift in understanding infinity and distance in these spaces.
So, we've been exploring non Euclidean geometry lately, and I'm fascinated by how different it is from what we're used to with Euclidean geometry. Did you know that the Pythagorean theorem actually changes in hyperbolic space?
I did. In hyperbolic geometry, instead of the familiar a squared plus b squared is equals to c squared, the equation is adjusted to a squared plus b squared is less than c squared due to the curved nature of the space. It's so intriguing because parallel lines eventually intersect, which is the complete opposite of what we see in Euclidean geometry. Why do you think this concept of parallel lines meeting is so significant in understanding non Euclidean geometry?
That's a good hot question. The idea of parallel lines intersecting in hyperbolic space fundamentally changes our understanding of infinity and distance. It challenges the parallel postulate in Euclidean geometry, which says that given a line and a point not on it, only one line can be drawn parallel to the original line through that point. In hyperbolic space, there are infinitely many such lines. This has implications in fields like cosmology, where understanding space curvature helps explain the shape of the universe. But what about elliptic geometry? What's different there?
In elliptic geometry, parallel lines don't exist at all. The sum of the angles in a triangle exceeds 180 degrees, which is mind-blowing if you are used to Euclidean standard. For example, if you imagine a triangle drawn on the surface of the Earth, like starting from the equator, heading north to the North Pole, and then making two 90 degrees turns, the total angle sum will exceed 180 degrees. How do you think this impacts real-world applications, such as navigation or cartography?
That's a very practical question. Understanding elliptic geometry is crucial to accurate navigation and mapping the Earth's surface. Since the Earth is approximately spherical, using Euclidean assumptions for long distance travel leads to inaccuracies. The concept of great circle routes, where the shortest path between 2 points on a sphere is an arc rather than a straight line, is derived from elliptic geometry. This deviation in angle sum is essential for plotting courses and understanding how distances work on a curved surface.
Exactly. And what's fascinating is how these non-Euclidean concepts help in modern technology too. For instance, GPS satellites rely on understanding of non-Euclidean geometry to provide accurate positioning. Do you think there are areas in art or architecture where these principles are applied as well?
Absolutely. In art, hyperbolic geometry has been used to create visually stunning and mathematically complex patterns. M.C. Escher, for instance, famously applied principles of hyperbolic space in some of his works to create tessellations that seem infinite. In architecture, non-Euclidean geometry allows for more organic and less rigid structures. Curved spaces inspired by hyperbolic geometry can be seen in modern fluid architectural designs. Here's a question for you. How do these different geometrical spaces challenges our traditional notion of what space and distance mean?
That's a deep one. Traditional Euclidean space has taught us that space is flat and distances are straightforward. But non-Euclidean geometries introduce the concept that space can be curved, either positively like a sphere or negatively like a hyperbolic plane. This shifts our understanding by showing that distance isn't always a straight line, and straight itself can be redefined. It makes us question that very fabric of space, how it bends, and what that means for everything from light traveling in space to the behavior of gravitational fields.
Right, and that ties into the bigger picture of how mathematics and physics intersect. For example, Einstein's theory of general relativity uses the concept of a curved space-time, which is more aligned with non-Euclidean geometry than with Euclidean. The idea that gravity isn't just a force, but the result of the curvature of space-time really turns classical mechanics on its head. So, in a way, learning about non-Euclidean geometries isn't just academic, it's essential for understanding the universe itself.
Well said. It's amazing how much deeper our understanding goes once we step outside the realm of flat, familiar spaces. One last hats. How do you think learning about non Euclidean geometries influences the way we approach problem solving in mathematics and other disciplines?
That's a thought provoking one. Studying non Euclidean geometries forces us to think beyond the boundaries of conventional logic. It teaches us that assumptions we take for granted might not hold in all cases, and that solutions may need to be approached from completely different angles. This shift in perspective is invaluable, not just in math but in fields like computer science, engineering, and theoretical physics, where thinking outside the Euclidean box can lead to groundbreaking discoveries.
Exactly. It's a reminder that the universe is more complex than our most intuitive ideas, and embracing that complexity can open up a world of new possibilities. The third topic is the legacy of Euclid and the evolution of geometrical thought. This topic examines Euclid's foundational work in geometry and how mathematicians like Gauss and Riemann expanded these ideas with non Euclidean geometries. It discusses the introduction of curved spaces, the concept of geodesics, and Riemann's influence on Einstein's theory of general relativity. Practical applications in GPS, global navigation, and understanding space-time curvature are highlighted, emphasizing how non-Euclidean ideas impact our modern world.
Did you know that Euclid's work, Elements, is still the foundation of what we know as geometry today? It's fascinating how these postulates laid the groundwork for everything we learn in basic geometry.
Absolutely. But what I find even more interesting is how in the 1800s, mathematicians like Gauss and Riemann started to challenge those foundational ideas and explore new types of geometries. Speaking of which, why do you think Gauss and Riemann's work was so groundbreaking?
That's a great question. Gauss and Riemann's work was groundbreaking because it introduced the idea that the shortest distance between 2 points, known as geodesic, could be curved, not straight. This challenged the Euclidean idea that a straight line is always the shortest path. By considering curvature, they expanded our understanding to include spherical and hyperbolic geometries. But here's something to think about. How does the concept of parallel lines change these non-Euclidean geometries?
Good point. In Euclidean geometry, parallel lines are defined as lines that never met no matter how far they are extended. However, in spherical geometry, there are no parallel lines at all. Every line eventually intersects. On the other hand, in hyperbolic geometry, an infinite number of lines can pass through a point and never meet a given line, making them parallel. This fundamentally changes our perspective or perception of space and distance. What do you think is the real world importance of understanding these non Euclidean geometries?
That's an insightful question. Understanding non-Euclidean geometries is crucial for real-world applications, like navigation and mapping. For example, when pilots and navigators plan routes over long distances, they need to account for the Earth's curvature, which is better represented by spherical geometry. This ensures that the straight line path they follow is actually the shortest path over a curved surface. Why do you think Raymond's contribution is often highlighted in discussions about non Euclidean space?
Raymond's contribution is highlighted because he expanded the concept of geometry to higher dimensions, which was revolutionary. He introduced the idea of Riemannian geometry, which allows us to study spaces that can be curved in complex ways, not just positively or negatively curved. This idea became the mathematical framework for Einstein's theory of general relativity, which describes how gravity affects the curvature of space-time. What implications do you think this had for mathematics and physics?
Raymond's work laid the foundation of modern physics. Without his contributions, Einstein wouldn't have been able to describe how massive objects warp the fabric of space time, leading to phenomena like black holes and gravitational waves. This changed how we understand gravity, not as a force but as a curvature of space time. So, learning about Euclidean geometries isn't just theoretical, it shapes our understanding of the universe. But here's a challenging question. If Euclidean geometry is based on flat space and non Euclidean geometries include curved spaces, what would be an example of geodesic in non Euclidean space?
That's a tricky one, but I'd say a geodesic in non-Euclidean space could be represented by the great circles on a sphere, like the equator and the lines of a longitude. This circle represents the shortest path between 2 points on the surface, even though they're curved. In hyperbolic space, geodesics can look like arcs that intersect the boundary of a desk at the right triangles. It's fascinating to think about how the concept of straight can change depending on the geometry. Can you think of an example where this might affect real world problem solving?
Yes, consider global positioning systems or GPS. GPS satellites orbit Earth in a curved space, and the calculations they use have to account for the curvature of both space and time, based on general relativity. If we only use Euclidean principles, we'd have inaccuracies in positioning. Non Euclidean geometries make GPS accurate and reliable. So, these theories aren't just abstract, they have practical impacts. What do you think is the biggest challenge when trying to visualize non Euclidean space?
I'd say the biggest challenge is overcoming the instinct to think in Euclidean terms. Our brains are wired to think of a space as flat. So imagining space where parallel lines intersect or the angles of a triangle exceed 180 degrees can be difficult. Tools like models of hyperbolic planes or simulations can help, but it still requires a big mental shift. Why do you think learning about these types of geometries is important for students today?
Learning about non-Euclidean geometries is important because it pushes students to think beyond the familiar and opens up new ways of problem solving. It enhances critical thinking by challenging assumptions and broadening perspectives, which is valuable not just in math but in any field that requires innovative thinking. Plus, with advances in technology and space exploration, understanding these concepts can prepare students for careers in physics, engineering, and data science. What do you think could be a good approach to help students better grasp non Euclidean concepts?
Hands on learning and visual aids are key. For instance, using 3D models of curved surfaces or interactive software that shows hyperbolic planes can make these ideas more tangible. Engaging in discussions and problem solving activities where students draw connections between theoretical concepts and practical applications can also be very effective. It's about making the abstract more accessible. Would you agree?
Absolutely. Connecting theory with real world applications make the learning process more impactful. By seeing how these mathematical ideas influence everything from space travel to art, students can appreciate the relevance of non Euclidean geometries. It's amazing how what started with Euclid over 2,300 years ago has evolved into a subject that can explain the universe itself.
For the fourth and the last topic, we have Beyond Euclid, the evolution of geometry through history and its impact of modern science. This topic explores geometry's progression from Euclidean foundations to modern breakthroughs in non-Euclidean geometries by mathematicians like Gauss and Riemann. Students discuss how these advancements led to practical applications in areas such as general relativity, GPS, and architecture, showing how challenging classical ideas drives innovation in understanding space and reality.
So, we've been learning about Euclid's elements and his five postulates. It's incredible how foundational his work has been to what we now call Euclidean geometry. But did you know his fifth postulate, the parallel postulate, sparked a lot of debate among later mathematicians?
Yes, I remember reading that. It's the postulate that states, given a line and a point not on that line, there is exactly one line parallel to that given line that passes through that point. But it's interesting. Why do you think Euclid's fifth postulate was so controversial compared to his other postulate?
That's a great question. The fifth postulate was more complex and seemed less intuitive than the others. Unlike the first four, which are more straightforward and almost self evident, the parallel postulate felt like it needed proof. Mathematicians struggled with it because it wasn't a simple questioning of the parallel postulate have on the field of geometry.
Excellent point. The skepticism around the parallel postulate led to the exploration of alternative geometries, which changed the entire landscape of mathematics. For instance, mathematicians like Gauss, Bolyai, and Lobachevsky developed hyperbolic geometry, where the parallel postulate doesn't hold. In hyperbolic geometry, There are infinite lines that pass through a point without intersecting a given line. This exploration proved that geometry isn't confined to flat Euclidean space. It challenged the notion that geometry had to adhere to Euclid's framework. Why do you think these non Euclidean geometries are significant today?
Good question. Now, Euclidean geometries have profound implications in various fields. For example, spherical geometry is crucial for navigation and understanding planetary motion, as the Earth's surface is not flat. Hyperbolic geometry has applications in areas like cosmology, where it helps model the universe shape and understand space time. Speaking of models, can you think of real world examples that illustrate these non Euclidean geometries?
Yes, a great example is spherical geometry when you're navigating Earth. If you draw a triangle on a globe with three 90-degree angles, the sum of the angles is more than 180 degrees, which defies Euclidean geometry. For hyperbolic geometry, think of certain artistic representations, like Escher's work, where space appears to curve infinitely inward. Here's another hot question. How do you think mathematicians were able to prove that Euclidean geometry wasn't the only valid system?
They started by assuming the opposite of Euclid's fifth postulate and saying if a consistent system could be created. When they discovered that consistent geometries were possible without the parallel postulate like in hyperbolic and spherical geometries, it proved that Euclidean geometry was just one of many possible models. This also led to the realization that our physical world doesn't strictly adhere to Euclidean rules, especially on larger scales, where curvature comes into play. So, how did Euclid's initial postulate inspire modern geometry?
Euclid's postulate laid the groundwork for logical reasoning and mathematical proof. They inspired mathematicians to think critically and explore the limits of axiomatic systems. This exploration led to breakthrough in understanding space, shapes, and dimensions. Raymond's work, for example, extended geometry to curved surfaces, which is foundational for Einstein's theory of general relativity. If we had to apply these non Euclidean principles in everyday life, where would we see them most?
That's an interesting one. In everyday life, non Euclidean principles are most evident in global navigation and mapping. Map projections that translate the Earth's surface onto flat paper have to account for spherical geometry, which explains why different maps show varying distances and shapes. In a more theoretical sense, technologies like GPS rely on algorithms that incorporate these geometric principles. Here's another hot challenge. How do you think the shift from Euclidean to non Euclidean thinking has influenced other fields of study?
The shift has had a huge impact. For example, in physics, the realization that space can be curved led to Einstein's general theory of relativity, which describes gravity as a curvature in space time rather than a force. This has changed how we understand the phenomena like black holes and the expansion of the universe. In art, non Euclidean geometries have influenced works that play with perspective and visual perception, making audiences question their understanding of space and form. The implications go beyond math and into our broader understanding of reality.
Agreed. It's amazing how one seemingly simple postulate led to such a profound shift in our understanding. Euclid's legacy is not just in what he accomplished, but in the questions his work inspired. And that's the true beauty of mathematics. It's not just about answers, but about the endless questions that arise.